did you say?
Yeah.
Okay. Chapter 2:17. There are two oxides of copper. One oxide has 20% oxygen by mass. The second oxide has a smaller
No, that's not it. On Pearson.
on mastering Chem. All right. Do you remember the name? What it asked for? Let me see if I can just go.
Yeah, it's about hydrogen.
Okay. Let's see if they make me sign in again. Yeah. All right, this is number 17, you said?
Yeah.
This is a little different. This is not the student view here. Okay, deuterium. Let's see. Let me get the student view. Deuterium is just hydrogen 2, and here's the mass at 4 decimal places, 2.0140 U. Is sometimes used to replace the principal hydrogen isotope, hydrogen 1, in chemical studies. The percent isotopic abundance of deuterium is 0.015%. In a lot of studies, what they try to do is they try to isotopically enrich certain samples. Like, for example, I work next door to a biochemistry lab, and in the biochemistry lab, they tried to artificially enrich their biological samples with phosphorus 32. Phosphorus 31 is the only naturally occurring isotope of phosphorus, so it's 100% phosphorus 31 in nature. So the mass of phosphorus there is the mass of all phosphorus atoms have that mass. There's no average, it's just 100% that mass. But that's naturally occurring isotopes. Phosphorus 32 is a synthetic isotope that's made using nuclear processes. It's radioactive. And they try to replace the phosphorus 31 with phosphorus 32 so they can follow the reaction. They're having some kind of biochemical reaction. So for example, does the phosphorus end up in DNA, or does the phosphorus end up in protein, or where does the phosphorus end up? And so they try to figure out where the phosphorus ends up by using a detector. They can detect the radioactive decay of the phosphorus and then follow it, as they want to better understand what we call the mechanics or the mechanism of how reactions occur. And so if you can understand the mechanics or the mechanism of how reactions undergo, how they occur, then you can better understand how things work. And also make predictions about how things work. But there's still a lot of unknowns. If they knew how everything worked, then they could just manufacture a perfect drug, to fix everything. If they can just predict, And so if you understood the theory at that level, right now there are two ways. Well, this goes for all fields of science, not just medicine, but It's trial and error. They just make a whole bunch of variations of the same thing. So they have microreactors with 10,000 like little wells, and they can just make tiny variations in different things. And mixtures as well, not just pure compounds, and they see how the mixtures interact with certain things. And this approach is the experimentalist approach. You just make it, see what happens kind of approach. And then you have the theoretical approach. The theoretical approach are guys or scientists on computers trying to model the system theoretically so that you don't have to make 10,000. You can just make one, and that one should be perfect, let's say. That would be quite nice. And so this brings up when I was at UCSB, do you know the inventor of the blue LED was there? The professor in physics. He won the Nobel Prize in physics. Actually, the physics department has a lot of Nobel Prize winners at UCSB. But there's a big search for the blue LED. So you had their theoreticians trying to predict what composition of ceramic will make a blue LED. And then you had your experimentalists trying. The experiments don't go into it blindly. They look at what the theoreticians are doing and then try to target something. But in the race for the blue LED, who won? Was it the theoreticians or the experimentalists that won in the race for the blue LED? The blue LED, the red LED has been around for a long time. That was the oldest one discovered. And then, I think 20 years ago or something, the green LED. And so we had the red LED and the green LED. But you know why everybody wanted the blue LED?
Because you can mix the three and make it color.
Yeah, you can mix the three colors to make any color in the rainbow. And so the blue LED was a huge, what do they call it? A huge goal, of scientists at that time. So there's a huge push to make the blue LED, and it was decades that people were working on the blue LED. And finally, this guy got it. And now we have LED light bulbs. We wouldn't have LED light bulbs if the blue LED wasn't discovered. And he did a combined approach. He was an experimentalist. But obviously he knew something about theory, otherwise you could be experimenting for forever. Well, anyway, so there's different things where we substitute. I used to use deuterium a lot. I used deuterium water. We called it deuterated water, heavy water. If it can be done with 100% efficiency, what mass of hydrogen gas would have to be processed to obtain a sample containing 2.70 times 10 to the 21 deuterium atoms? And so if we could just make this, is this the question here? So when we make a hydrogen molecule, how many hydrogens do we bind together? 2. So you have a choice, H1 or H2. Most likely you're going to pick an H1. And then for the second one, H1 or H2? Most likely a H1. Very rarely will you have an H2 and an H2, but it happens. You can get an H2H2. Now what you need to do with the H2H2 is you need to separate it out from all the others. And now you have 100% H2H2. So if you have 100% H2H2, so I think that's what they mean by 100% efficiency. So we isolated the H2H2. What mass of hydrogen gas would have to be processed? And so this is just, will be for dimensional analysis. This 100% efficiency, we don't need to put in because, and normally we automatically will deal with percentages, but in this instance, this percentage I'm not going to worry about because it's 100%. So that just means we do not have to account for all of the other variations. H1, 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 H2, H2, H1. How many different hydrogen molecules exist in nature? 4, yeah. And so we ignore the other 3 and focus on 100% H2H2. And so a problem like this, although I'm sure a lot of people, actually, how many people got this one? Nobody? Okay. So what we have is we just have dimensional analysis. 2.7 times 10 to the 21 H2 atoms. And when we have a number of particles, we typically don't work with individual particles. We typically work with moles of particles. So the first thing I'm going to do is I'm just going to convert this to moles. So we'll have this many H2 atoms per mole of H2 atoms. That gets rid of the H2 atoms, deuterium column. All right, now I'm at moles, so where can I go from moles? What I can do is, what is a formula? A chemical formula is a mass ratio or mole ratio? Mole ratio. And so I just use the composition of hydrogen gas. Hydrogen gas is diatomic. And so I say 1 mole of H2, 2. And so that's diatomic hydrogen. Has how many moles of H2 atoms? 2 moles of H2 atoms. And then I know the mass of H2 atoms to 4 decimal places. 2.014 U, but I don't have to use U. I could use the other unit. What's the other unit? The other unit would be grams. So I'm just going to use the grams. I could do U per atom, but I don't want to do U per atom. Actually, I'll just paste this somewhere here. So rather than saying, I'm just going to say grams per mole for deuterium, hydrogen 2. Actually, nobody calls it hydrogen 2. Everybody calls it deuterium. Deuterium. Yes, DEU. And so I have 2 of these. And so I have to double that. So I think I could double that in my head. 4.0280 grams per mole. So this is for the deuterated hydrogen molecule, per mole of deuterated hydrogen molecule. That's what we call it, deuterated. So we call it deuterated water, D2O. The oxygen isotope can vary, you know. I was using it because deuterium is invisible to magnets, and whereas hydrogen ones are visible to magnets. So I was doing magnetic resonance type stuff. So let's calculate how many grams. It's going to weigh more than hydrogen, the average hydrogen. So 2.7 times 10 to the 21 divided by 6.022 times 10 to the 23 divided by 2 times 4.028. 9.029 times 10 to the minus 3 grams, or 9.029 milligrams, or 9.03 milligrams of deuterated hydrogen molecule. Uh-huh.
I'm still kind of confused why we didn't use the percent abundance of like deuterium. Like what is the 100% efficiency?
says that's wrong.
It says it's wrong? That's odd. I would double check my calculation. Well, let me answer this question first, and then we'll look at that. Why didn't we use 100% efficiency? That's because if you had a sample of hydrogen, just H2, then we would use it if, let's say, if 50% of the hydrogen was deuterated, or 1% of the hydrogen was deuterated. And so we would use the percent efficiency as like a percent natural abundance. And so this is what I'm assuming that they're saying, although it's not entirely clear. I'm assuming that this is the new percent abundance.
So we can just have a bunch of hydrogen and all of them are deuterium.
And all of them are deuterium. Correct. So, oh, I see. I didn't read this carefully enough. I thought that they were asking what mass. They say what mass of hydrogen gas would have to be processed. So I was thinking, okay, if this is 100% efficiency, what mass of hydrogen gas has to be processed? Okay.
I was having a hard time figuring out where to plug in the 0.015%.
Yeah, and so this would be it. They're saying that, I was assuming that they had already separated. And so, for example, the molecules that we're going to have are H2H2. This is going to be least abundant. And then we're going to have H2H1, H1, H2, and the most abundant will be H1H1. And so the 100% efficiency threw me off because I already assumed that they have collected and isolated the H2H2 because we're going to form very little H2H2, correct? Correct. But the 100% efficiency just refers to this. When you transferred your crystals over from the beaker, did you get 100% of the crystals from the beaker into the cellus crucible? That's 100% efficiency, you know. But the percentages threw me off because we have to figure out, and this is where we need the other percentage. The other percentage is going to come in here. And so do you guys remember how to calculate the percent abundance of each of these? And so we'll do that right now. And so what is the percent abundance of H2H2? The percent abundance of H2H2, we don't do a percent times a percent. What do we do?
Fraction.
We'll do, the first one we'll do as a fraction.
0.015.
Oh, 15. 15. And the second one we'll leave as a percent. And so the percent abundance of H2H2 is going to be 0.015 divided by 100 times 0.015. I don't, you know, I could change it. I could just do 0.015 squared, but I don't because I make more mistakes that way when I try to do the math in my head, so I just punch it in the calculator. So you might think that's not that efficient. But this comes out to 2.25 times 10 to the minus 6%. And so I like to put these percentages into perspective. So you don't have to do this. You know, this is an aside. We don't have to do this. But the only reason I do this is to try to visualize how many deuteriums there are in a sample of hydrogen. And so if I do this, I'll do actually, I'm not going to do it like that. I'm going to do it like this. I'm going to say that there's okay, I need 5 zeros. 1, 2, 3, 4, 5 zeros and a 225 out of 100. And then what I do is I move the decimal so to make this a whole number because we can't have fractions of molecules. So I'm going to move this 1 2, 3, 4, 5, 6, 7, 8 places. So I'll need to move this 1, 2, 3, 4, 5, 6, 7, 8. And then add zeros here. Or actually, don't add them yet. And so this is going to be 225. And so I have 8, 9, 10 zeros. So 1 and then 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I'll try to figure out what this number is. So how many is that on the bottom? 10, what is it?
10 billion.
10 billion?
Yeah.
Okay, so what this says is that out of 10 billion hydrogen molecules, how many of these will be H2H2? How many? 225. So that's another way we could do this. So in this case, I'm just going to leave it as molecules because these percent abundances are usually in terms of particles, not mass, remember? You could do these in moles too. Like, so for example, if I had 10 billion dozen hydrogen molecules, then I would have 225 dozen H2H2, right? And so a dozen is like a mole, it's just a counting unit. So this is a mole ratio or mole fraction or an atom or particulate fraction. It's not a mass fraction though, correct? And so that means I have to redo the problem because I misunderstood the problem. And so the problem was if I have 2.70 times 10 to the 21 deuterium atoms, times 10 to the 21. This is an odd question because normally they wouldn't say deuterium atoms because we know how many molecules there are. And it would just be easier to say how many of these molecules there are rather than calling it. Like say, I have 100 hydrogen molecules. Oh, that's 200 hydrogen atoms. Do you call 100 hydrogen molecules 200 hydrogen atoms? So that's another thing that threw me off on this problem because normally I wouldn't call 100 hydrogen molecules 200 hydrogen atoms. So it's weird. This problem's weird. But anyway, I can't be too choosy about these types of things. So what we're going to do is I'm just going to do this. I'm just going to say that there are 2 deuterium atoms per H2 molecule. Okay, that means the deuterium atoms are going to cancel out. So this is like I have 200 hydrogen atoms. How many hydrogen molecules do I have? 100. No, because each hydrogen molecule contains 2 atoms. Okay, and then where would I go from here? Then I would go to moles. Okay.
1 mole of 6.022 times 10 to the 23rd.
Okay, 1 mole of H2 molecules is 6.022 times 10 to the 23rd H2 molecules. Okay, so the individual molecules cancel out, and I'm left with moles of H2 molecules, and then where would I go from here? Grams? Okay, I could go to grams, and so it was 2.0280, was that correct? Let me scroll up. No, 4.0280, sorry. 4.0280 grams of H2 per mole of H2H2. Oh, this is a good problem. And then where would I go from here?
So is it a weird problem or is it good?
Well, this is good because so many common errors are made in this problem, this type of problem. Where would I go from here?
You're not done?
Isn't it asking for grams of hydrogen?
It's asking for grams of hydrogen. And it's asking, what they're going to do is they're going to take all the hydrogen and then try to extract just the H2H2 out of there. And so I would need 10 billion H2 molecules just to get 225 H2H2 molecules. And those 225 H2H2 molecules would give me 450 H2 atoms. But I don't want 450 H2 atoms. I want some large number, 2.70 times 10 to the 21 H2 atoms. If I want 2.7 times 10 to the 21 H2 atoms, I'm going to have to process a heck of a lot more than 10 billion. And do you count? No, we don't count them. In fact, what's much easier than, can you count the individual hydrogen molecule? No, what we're going to do is weigh them. You know, we could weigh gases. It's not so easy, but it's not so hard either in containers. You can weigh them, compress them. Like you can easily tell if your spray can goes empty, right? If you have some air, like the compressed air ones, because it weighs a lot less. And so all we're going to do is, okay, now if I stop here, let's see, if I stop here, I know how many H2 molecules. If I stop here, I'll have the moles. Okay, then if I stop here, I'll have the grams. Okay, so now where can I go from here?
Did you do the percent?
Yeah, so this is the next step. I would probably go to percent, right? I just calculated my percentage right here. So I'm going to use that percentage here. That is, there are, out of 100 H2 molecules, there are 2.25 times 10 to the minus 6 that are deuterated, completely deuterated. And this is why, you know, this is why I get on people for not writing the units. You know, if you don't write units in this class, then you're not going to be successful. So I didn't write units here for the percentage because I assumed everybody knows what this percentage is. But I wrote them over here. What are the units for this percentage?
Molecules of hydrogen gas?
Yeah, this would be the percent of the deuterated. This is 100% deuterated molecules. Or when they're talking about percentages, you know, they're different percentages. They're saying that they can, if they have a sample of hydrogen, when they're saying 100% efficiency, that means they extract every one of the deuterated hydrogen molecules out of there, and don't leave any behind. This is like saying you extracted every single white crystal out of your beaker and didn't leave any behind. That's 100% efficiency in that. And so what they're saying is they isolated with 100% efficiency. So that's what the 100% efficiency is. But this is not going to work. Do you see why this is not going to work? this is not going to work because this is not grams. This is not out of 100 grams, I have 2.25 times 10 to the minus 6 grams. It's not grams. This is a percent by mole or percent by particle. And so I can't use this. Is there another percentage I can use? If I knew the mass percent, let's say I had a 10 billion grams of hydrogen gas, how many grams of deuterated hydrogen molecules? If I knew that percentage, then I'm fine. You have to be aware of this because air that we're breathing is 21% oxygen. Does that mean in 100 grams of air I have 21 grams of oxygen? True or false?
False.
That's false. I'd actually have more than 21 grams. So when they say air is 21% oxygen, what are they talking about? What they're talking about is if I have 100 air molecules, nitrogen, oxygen, whatever else, then 21 of those 100 molecules will be oxygen. And so there are two different percentages that people confuse all the time, and then on the tests I see this all the time. People don't pay attention to the units, and so they're using a mass percentage when they should have been using mole percentage, or they're using a mole percentage when they should have been using a mass percentage because they just don't know the difference between these important percentages, you know. So when I asked people, you know, so many people write grams. Not so many, maybe 5%. 5% of the people will write grams. So they'll put grams over grams. So what is this? 5 zeros, 2.25 times 10 minus 6 grams of deuterated hydrogen per 100 grams of hydrogen molecules. That's totally wrong, unfortunately, and then I have to deduct points, but
The reason, like, for the one using air is because certain, like, air molecules are heavier than others, but you're talking about the percentage of how many of those there are.
yeah, so if you look at everybody knows the volume and the mole percent of air, but not that many people have the mass percent of air because mass percent of air is not as useful, I guess. And so if we go to the percent composition of air, do they tell you if that's a mass percentage or mole percentage? They don't tell you. It's important to know that. But that turns out that that is a mole or particle percentage. You know, here's the breakdown, and there's argon, a little bit of argon. And then they have this pie chart here, the composition of air. But, and so that's a problem. The problem is they assume you know already. But if you're just learning, if you're just a beginner, you don't know, right? And then a lot of people, they don't go beyond that. And so if we look at the mass percent composition of air, oops. I get this, but this is wrong. This is not the mass percent composition of air, nor is this the mass percent composition of air. This is the mass percent composition of air. Here. If you do it by mass, then if I had 100 grams of air, 23.2 grams of that would be oxygen. Oxygen's a bit heavier than nitrogen. Oxygen's 32, nitrogen's 28. And so it's going to be slightly biased towards oxygen since it's heavier. The percentage oxygen goes up because it's heavier, and the percentage nitrogen goes down because it's lighter. And so you got to be careful. And so that's one of the first things I look at. Whenever I have a percentage, part per million, part per billion, part per trillion, the first thing I look at, is it by mass or is it by mole or particles or molecules or atoms? So when they're saying, okay, you know, the max is 10 parts per billion carbon monoxide, what are they talking about? You know, OSHA says you shouldn't have more than 10 parts per billion carbon monoxide in the space for 8 hours. That exceeds OSHA limits. And And so, anyway, the point is for dimensional analysis, you may get stuck. You may do the wrong thing. But, you know, do you freeze and do you give up? No. If you go down the wrong, if you're lost in the jungle or if you're lost in the desert and nobody's coming to rescue you, and you go down the wrong path and you're going down this little canyon and all of a sudden the canyon ends and you can't go any farther, what do? Do you just freeze there and stop? No, you would back up and then try a different canyon, you know, or different route or something. And so here, yeah, it didn't work, but we're going to try different. This one didn't work, so we're going to back up. How far should we back up? This one's not going to work because we don't have something that is a mass percentage. If we had something that's mass percentage, this would have worked. We'll just throw in the mass percentage and I'd be done with the problem. If I knew how many grams of deuterated hydrogen there were in 100 grams of hydrogen, I'm done. This is the final step. But I don't have that, and so how far should I back up? Well, if you're getting stuck, just back up to the beginning and try a different path. The different path, you don't have that many paths. You know, there aren't an infinite number of conversion factors that you can use. There's only 2, maybe 1, 2, maybe 3 at the most. I've never seen more than 3 forks that you can go down. So if fork 1 doesn't work, try fork 2. If fork 2 doesn't work, try fork 3. And so we'll just start this problem over again. Some people say, oh, you know, oh, you must not know chemistry very well. You know, I've gotten that comment a lot. Oh, you made a mistake, you know. But in science, it's like that. In science, you know, people try different things and like this NASA astrobiologist, even though it was a very interesting, an alternate life form, but it turned out it was a mistake. But that happens in science, and that's the beauty of the scientific method, is being able to catch and correct mistakes. And that's by the peer review process, so I'm glad somebody checked it. What is it, 10 to the 20th or 10 to the 21? 10 to the 21. All right, where do you want to take this next? We can go from, we have different paths. What are all the different paths we can take? So if I'm here, I could go to U. And so, for example, I could say that there are 4.0280 U per deuterium atom. Or not 4.280, it's 1.20140, sorry. 1.0140. U per deuterium atom. We could try this path. We didn't try it, right? What are the other paths that we could take?
You mean the different combinations?
No, different conversion factors. The other path we could take was that there was one H2 molecule requires 2 H2 atoms. The formula is a mole ratio or an atom ratio. And so I did moles earlier. This time I can do atoms instead. And so for each deuterated hydrogen molecule, we have 2 deuterium atoms. Right? That's pretty simple, correct? All right, think of another path that we can take from here. Right.
Could it be like 100 hydrogen atoms per 0.015 deuterium atom?
Yeah, we could do that one too. That's a good one also as well. And it's like, solving these problems is like, there's not just one path. Like a maze only has one correct path, but actually a maze, no, maybe it could have multiple paths. It depends on who makes that maze. But anyway, there are different ways to solve the same problem, especially with these types of ones. And so if we have 100 H atoms, then 0.015 of those will be deuterium atom. Well, it doesn't make sense to have 15 thousandths of a deuterium. So this is why I like to move it here, because having a partial atom doesn't make sense to me. And so when I see this, it looks weird. And so what I do is I say 15 out of what? And so move this 3 over. 15 out of 100,000. And so there are 15 deuteriums in 100,000 hydrogen. It would be the same ratio. You don't have to change it. It's not necessary. But sometimes I do that. It's an extra step of complication, so it's an extra place you might make a mistake. So it's maybe not worth doing. But to visualize this concentration, you might do it. Okay, and then where should we go? Are there any other paths you can think of? Anybody? No? Okay. Which path do you want to take? Path 1, 2, or 3? I definitely would not want to take path 1. Why? I definitely wouldn't want to take path 1 because it's taking me along the mass path, and I don't have the mass percentage. If I had the mass percentage, then I'm going to go towards mass. Instead I have an atom or mole percentage. Well, I could take path 2 and then maybe a different fork later. And so if I want path 2, this is what I would have done. I would have gone path 2 and from here, I would have done it differently. A percent abundance is,
Couldn't we use the percent abundance to find like a conversion factor that would work?
Yeah, and we already have the conversion factor that would work here. I'll just write it. So path 2, what I would have done was I would have backed up from here. And then I would have taken a different path from here. The different path from here would be, we have a conversion factor here that gets rid of moles of hydrogen molecules. And what is that conversion factor? That conversion factor is you have to know all the units for this percentage. And so let me write them here. This is going to be, it's percent. And so this is going to be percent by molecule. And so this would be molecule of deuterated hydrogen per 100 molecules of hydrogen. Or you could have a dozen. So for example, I could have a dozen deuterated hydrogen molecules over 100 dozen hydrogen molecules. Or I could have moles of hydrogen molecules over moles of deuterated hydrogen molecules over moles of hydrogen molecules. And so when I see this percentage, I already have figured these out. I already know these, so when I do my dimensional analysis, I know these 3 options are there available for me to take. And so when I get to this fork, That's what I would have done. I would have said, okay, I know how to get rid of moles of deuterated hydrogen molecules. And so they're going to be, I'll just write it like this, 10 billion. And so they're only going to be 225 deuterated hydrogen molecules out of 10 billion hydrogens. Okay, where would you go next from here? Because now the deuterated hydrogen molecules cancel. And that leaves me with just the number of hydrogen molecules. So if I have the number of hydrogen molecules, how many different paths are there from here? There's only one I can think of. Well, actually, not one. There's more than one. Should I go to grams of hydrogen molecules? Because do you know what the average hydrogen molecule weighs? 1.008 times 2. So the average hydrogen molecule weighs 2.016. So, okay, I'll go that way. I'm going to go 2.016 grams. Or actually, that's not grams. This should be U. Because I'm dealing with, this is grams per mole, right? So this is one route I can go. I can go 2.016 U of hydrogen for every H2 molecule. So this is the average mass of a hydrogen molecule. Average hydrogen molecule was 2.016 U. Okay, then where can I go? How many U in a gram? Everybody should have this memorized. You've had, what, over a week to memorize it. How many U in a gram? Actually, you don't need to memorize it because you could easily derive it. And let me tell you, I've asked people to derive it on past exams. How do you derive the relationship between the U and the gram? Kind of, yeah, it does. Avogadro's is involved in it. Anybody? Avogadro, what do you do with Avogadro's? So, right. So what you want to do is, in preparation for the exam, this is what my goal was as a student, is I try to understand everything that was discussed in lecture. So if I didn't understand the relationship between the gram and the U, I talked about the relationship between the gram and the U, then what I do is I'd read the book, I'd look on wherever, other sources, you can check the internet, and if still that didn't make sense, I'd ask. I'd ask the TA, and then I'd ask the professor. Because when you go into the exam, you want to understand all the concepts that were presented in class. Otherwise, let me tell you the exam structure at UCLA. And you saw my exams, right? I try to limit the point value of the questions. At UCLA, my typical class had 4 questions. Each question was worth 25 points. If you blew one question, you're already down to max of 75%.
I don't think we have seen past exams.
Have you guys seen it?
No, I don't think so.
You didn't see it? Let me check the post. I posted it last week. At least I thought I posted it last week. The link is working. I post things on Canvas. You check the Canvas? Yeah, I posted on Canvas last week. Here, sample old exam 1. But when you look at it, and some people have already asked me, there's mixed multiple choice. I told you at UCLA, the only multiple choice exam I had was for paleontology, which was known as the easiest life science class there. But most of the tests I had, they only had like 4 questions. That was typical, 4 questions. And the 4 questions, what should you study? Because if you don't study that, thinking, maybe they're not going to ask that, then you get surprised. So let's say 125-pointer was discuss the relationship between the gram and the AMU. And you didn't study that. And that's, wow, 25 points gone right there. It's a harsh hit. I didn't like that at all. And so that's why, I totally changed the way I study. I tried to make sure I understood everything. And I didn't say, he's probably not going to ask that. Well, he might. But if it was asked, then you get lucky. Because if you at least understand the concepts before, then you're okay. And so if I ask the relationship between the gram and U, it should be quick recall. What's the relationship between the gram and the U? I spent like 10 minutes in class talking about it. Or 5 minutes, maybe it was 5 minutes. But 5 minutes out of 1 hour and 30 minutes is a significant percentage, I think. So anyway, let me tell you what it is. It's an easy number to remember, but how do you derive it? And so we derived it in class. And so we could go straight to grams. And so we know that 1 gram is 6.022 times 10 to the 23rd U. And that comes from the definition of the mole and the definition of the AMU combined using dimensional analysis. And so here we're at grams of hydrogen. And so is that what they want in this particular problem? Yeah. They want grams of hydrogen. Now, this might seem like a really complex way to do it, but there could be an easier path. So let's say you forgot the definition of the U. Is there an easier path to the same answer? So even if I got stuck and I couldn't remember how many grams were in a U or how many U were in a gram, then you try to find an alternate path. Because a lot of these problems have multiple paths that lead you to the same answer. And these are correct paths. And so the alternate path I could have done is I could have branched off here. This is one way to branch. But the other way I could have branched off is like this. And so this is one way. Another way I might have branched off is by going here, Avogadro's number. And so I would have just went ahead and done this. In fact, I would have probably not done path A. I would have done path B because I don't like U. Because we don't deal in U most of the time. Unless you work with individual molecules, you deal with U. If we work with individual molecules, then we don't take the average hydrogen molecule. We look at the specific isotopic composition of that hydrogen molecule. And so if I use U, then I'm looking at not the average, I'm looking at like H2H2, H2H1, H1H2, H1H1, right? And so I stay away from U when we look at averages. I much prefer to use grams. And so in order to go to grams, what I'm going to do is I'm going to go from H2 molecules, and then I'm just going to use Avogadro's number. There's going to be a mole of H2s for every 6.022 times 10 to the 23rd H2 molecules. And these are average, and so that's fine, because mole's a huge number. And then I'm going to go here. I'm just going to say that there are 2.016 grams of hydrogen for every mole of hydrogen. And so myself, I would have preferred path B rather than path A, but it doesn't matter. Path A is perfectly fine. Works as well. But you might have gotten stuck because if you couldn't go beyond U, then you back up and try a different path. And so we could do this here. And this would take us to grams as well. But do you see we'll get the exact same number because we're multiplying by 2.016 and dividing by 6.022 times 10 to the 23rd. But this isn't the only way we could have done this particular problem because there was another branch here at the bottom here that we could have done. And this branch down here would have saved us having to calculate the percent natural abundance of the molecule here. And so let's say I forgot how to calculate the percent natural abundance of a molecule where you have to go fraction, maybe fraction times a percent or fraction times a percent, right? And so if we took branch 3, we don't have to know how to derive this. And so let's do branch 3 here. 2.70 times 10 to the 22nd.
8.
Oh, 10 to the 21st, yeah. I'm sorry, what was that?
2.80.
2.80, thanks. Was it 2.80? Okay, Mastering Chem does this, it scrambles the numbers. So just be aware of that. If you're using your friend's number answer, it might be different because the starting number might be different. Yeah. So Tristan, you probably had 2.8. I got 2.7. So I'll just stick with 2.7 in this particular problem. So 2.7 times 10 squared, 10 to the 21st deuterium atoms. Okay, if we take this branch saves me from having, and this is a very good branch that Holly mentioned, is if we just use the number outright, then I don't have to calculate the other thing. And so for every 100 hydrogen atoms, or 100,000 hydrogen atoms, I have 15 deuteriums. So for every 100, I'll have 0.015 deuterium atoms. And so this gives me the ratio of how many hydrogen atoms I need. And then where would I go from here? I could go to U, because I know how much the hydrogen atom weighs. It weighs 1.008 U. Do I want to go that route? No, I'm going to go where? You tell me. So if I have the number, the most logical place to go when you have the number of atoms is to convert it to moles. Why convert it to moles? Because we don't have to go to U. We can go to grams. Grams are much easier to deal with than U. And so I'm going to use Avogadro's number here, 6.022 times 10 to the 23rd average hydrogen atoms per mole of H atoms. And this is just asking how many grams of hydrogen? How many grams of hydrogen gas? Okay. This step is not necessary because the mass of 2 hydrogen atoms is the same as the mass of an H2 molecule. But we're going to do this. Hydrogen gas consists of diatomic hydrogen. And so we're going to say that there are, in 1 mole of hydrogen, there are how many moles of hydrogen atoms? 2 moles of hydrogen atoms.
Hydrogen gas.
I'm sorry? And so the moles of hydrogen atoms cancel, and that leaves us with moles of H2. And H2 is a gas normally under room temperature. It takes a lot to liquefy hydrogen, and so liquid hydrogen doesn't occur until you have very low temperatures, or alternatively, liquid hydrogen doesn't happen until you have very high pressures. And so the hydrogen stations that they have for the fuel cell cars, this is extremely high pressure. And so that's something to worry about. 2.7 times 10 to the 21 times 100 divided by 0.015 divided by 6.022 times 10 to the 23rd divided by 2. Oh, this gives me moles. I don't want moles. What do I want? Grams. And so it's going to be 2.016 grams of hydrogen, average hydrogens per mole. So I use the 1.008 to give me 4 sig figs. And so for hydrogen, I'm going to use 2.016 to give me 4 sig figs. Although I'm only allowed 3 sig figs in the end. So times 2.016. And so all three should give us the same answer, 30.1, if I did it correctly, the calculation. 30.1 grams of hydrogen gas. You can check it if you want. Here. So, like I was saying before, you have to adjust your studying depending on what kind of tests you have. You know. And I always thought those were cruel tests, you know, because you just don't study one thing and ouch, you get hit hard. I never liked that, but that's the way it is for some classes. So just be aware. My test, on the other hand, could be cruel as well. I'm sure lots of people think it's cruel. But I try to keep the point value a little lower so that if you don't know something, it doesn't kill you on the test as far as points. So. And then if you don't know something, I give partial credit. A lot of tests I had, there was 0 partial credit. So here, I mean, if it's 0 partial credit, your strategy might be a little different, you know. But if there's partial credit, then you should try to string together. If you can't get the final answer, then try to string together as many conversion factors as possible, but make sure they cancel. Because if you start throwing random conversion factors together, like some people do, I can't give you credit for that. Like people get grams squared or percent cubed or all kinds of weird units. Just try to make sure it's logical, and then I can follow it.
What's your advice for the part of the exam where we can't get partial credit, which is the
You can't get partial credit, and the multiple choice is low point value. Sorry, the multiple choice is you have the thing about this is you have most of these you have a 50% chance or 25% chance of guessing it. And then if you add in, like say you can eliminate, the thing is, if you can't get the answer, then do process of elimination. Try to eliminate the ones that don't, you know, that obviously don't. And so normally there are those. And so you would just take your best educated guess. And so a lot of people say with multiple choice, even with 4, you can probably eliminate 2, which gives you a 50-50 chance of guessing it. Yeah. Even though I say that, I saw the lowest multiple choice score I'd ever seen, like maybe 3 years ago, 4 years ago, where a person got 1 question out of 29 right. And I thought, how did that, you know, it's a spectrum. How do you do that? Even if you guess, you think you'd randomly be able to get 25%, you know, but how do you get less than that? And so it just, what can you do? I mean, you can't do much, you know, in that scenario. But there are different strategies. When you take certain tests, like say, for example, I don't know if the MCAT does this, but there are penalties for guessing the wrong answer. And so I think the MCAT is one that does this. If you guess the wrong answer, they deduct points. And so you have to have a really good certainty that you have the right answer before marking it in, or otherwise you start losing points. And technically, you can get, that person, the lowest they could get is 0 out of 29, but technically you could get less than 0 because of the negative. On the GRE, when I took the GRE Chem test, for each wrong answer, they deducted a quarter point. And each question was worth 1 point. I think it was a quarter point. And so you had to be careful because 4 wrong answers would cancel out 1 correct answer.
What answer did you actually get for this?
30.1 is what I got. But you know, what you do is, I try to give enough time to double check. So you should double check. I didn't double check this because you can double check it for me. Uh-huh.
I was gonna ask, I see this, the example only has multiple choice on it. I was gonna ask, do we only have a portion of our test that's multiple choice?
Yeah, but bring a small Scantron. You can actually bring a big Scantron. This has more multiple choice. Do you know which Scantron I'd like? This is a 4. They sell these at the bookstore. They also have these at the library. I want you to bring the 82E Scantron. 882E, E for A, B, C, D, E. 5. Where you'd have a 20% chance, yes. Yeah, like a big pack at the bookstore. Or, I think the bookstore, they're not that expensive. At the library, they're kind of expensive. I think they're 25 cents each or $1 each or something, I forgot. Out of the vending machine. But can you bring a Scantron like this? Okay. And then you're going to have free response questions. Actually, did anybody look at this? Or nobody noticed this? You did? Okay, you did.
Maybe you could send the email again?
Email?
Yeah, not like for this exam.
Yeah. Well, that makes things more complicated, and then I start forgetting and then some people end up dropping and they're still on the email list, or some people aren't. I don't know. They don't check their El Camino email. They only check their personal email. So, and some people don't check their email every day. And so then I get people asking me to do different things. I get lots of that. So it's going to just be posted, and usually I'll try to post it before the test. And then just take a quick. I thought Canvas sent out an alert when there was a change or something on the Canvas page. It doesn't send out any alert.
In the final.
These are all discussion sections. So what I did was I made this a discussion rather than a module, and so you could reply to this regarding the test. So if there are any questions about the test, you reply here, and then I can answer it here if you want, or in class, And so I'm doing things a little bit differently. In Chem 4, I had a separate. I also posted it in Chem 4 on Canvas as well, but I made a separate page. But this is faster if I don't have to make a separate page, because I have to do it for two sections, 2 classes. So once in a while, just check Canvas and see if there's any stuff or if there's any discussion regarding the test or that kind of thing. All right, so you can check all the methods. There are more that we could use to solve it, but the point is, don't give up too easily. That's the point. A lot of people, when I say a lot, more than there should be. I think on this test that I posted on Canvas, maybe about 5 people completely blank. Didn't know where to start. Just don't know where to start. Just start anywhere. Just pretend that there's nobody coming out to rescue you. And just try something, anything. Just throw it out there. Although maybe they think, oh, maybe there's going to be a dropped exam or extra credit or something as a rescue. But you can't always rely on that because there isn't always extra credit or bonus points or that kind of stuff. But anyway, I need to talk about chapter 4. So we talked about some of the stuff in the book. Let me continue where we had left off last time, and then I'm going to get into chapter 4. Chapter 4 is a lot of review as well as these. One thing that isn't so much review is the combustion analysis. So let's finish looking at the combustion analysis problems from the book. Let me tell you, at UCLA, they compress the first 4 chapters of our book into 1 chapter, and then they skip it. They say it's all review. If you look at their textbook, it's a majors, and they give they use the chem majors textbook for all majors, whether you're bio or not. And so it was kind of a jolt when I transferred. I transferred to UCLA. It was a jolt. And they warned us about this jolt. They said, oh, your GPA is going to drop when you transfer. And it did. Actually, they were accurate. They dropped 1. So I had to, I wanted to bring it back up. Since I know, but you can. You just have to prepare differently for different types of tests. So anyway, this is a hydrocarbon. It just gets CO2 and water. This was a carbon, hydrogen, oxygen. So we're going to get CO2 and water. Then we have to use the mass differences to calculate the grams of oxygen, which we talked about. This is a carbon, hydrogen, sulfur. And all the sulfur burns to sulfur dioxide. So we don't have to worry about other oxides of sulfur occurring. It's all going to go to sulfur dioxide. Oddly enough, sulfur dioxide is not complete. What is complete combustion of sulfur? Sulfur. Complete combustion. If you were to burn sulfur completely, what should it burn to? It would be sulfur trioxide because sulfur trioxide has an oxidation number of 6. 6 is the max for sulfur. And so, but it's okay. It doesn't go to sulfur trioxide. It just goes to sulfur dioxide, and this is fine. However, when we have nitrogen in there, nitrogen is a lot messier. And so when we have nitrogen in there, where's nitrogen? Okay, this is carbon, hydrogen, oxygen, carbon, hydrogen, oxygen, carbon, hydrogen, oxygen, carbon, hydrogen, sulfur. So again, the sulfur burns to sulfur dioxide, so we can figure it out. Where was the nitrogen? Nitrogen's a lot messier. And so this is a weird problem because here they burn the sample and they get the carbon dioxide in the water. From the carbon dioxide in the water, they can figure out how much carbon they have and how much hydrogen they have. But nitrogen's different. When you burn nitrogen, it makes a mess. You get all kinds of oxides of nitrogen. And so what they do is they have to do further processing. They take all these oxides of nitrogen, and this is what your catalytic converter does. A catalytic converter in a car takes all those oxides of nitrogen, which they call NOx, N-O-X. Have you heard NOx? When you go, if you have a car, like an ICE internal combustion engine car, you have to get it smogged every 2 years. And one of the things they check in the smog check is how much NOx emissions you have, oxides of nitrogen. What happens is those NOx go into the catalytic converter, and in the catalytic converter, the NOx are converted into nitrogen gas. Well, nitrogen gas, that's great, because what would you rather breathe? Nitrogen gas, which is what they call a pseudo-inert gas, or a pseudo-noble gas, or NOx. You'd much rather breathe nitrogen. You're already breathing nitrogen. And so What we do is we take a separate sample and have to totally do different chemical reactions here, burn it, take all the NOx, and then convert it back down to nitrogen using a catalytic converter, and then collect the nitrogen and see how many grams of nitrogen formed. And so this grams of nitrogen can be converted into moles of nitrogen gas, and moles of nitrogen gas can be converted into moles of nitrogen atoms. And so once we have moles of nitrogen atoms, or we don't do that. Here, the other thing is, we don't know how many moles of carbon and how many moles of hydrogen we have in this sample because this is a totally different sample. So what we have to do is we have to get the percent by mass nitrogen. If we know the percent by mass nitrogen, then we can take this sample and then figure out how many grams of this must have been nitrogen. Does that make sense? And then go from grams of nitrogen to moles of nitrogen, and then we get it. So this is the most complicated one, 45, because there's multiple extra steps here. But this is what I do. This is what I would do looking at the homework problems. I'd go through them, log them in my head, and then see, how do we solve them? And then if I can't figure it out, if I look at this and I go, I can't figure it out, and it's taking too much time, I grab the solutions guide and look at it, and then log that in my head. So if I'm ever hit with something, let's say there's phosphorus, then I'd know what to do. I mean, phosphorus, no big deal. They're probably going to burn it to some kind of oxide of phosphorus, right? And so that prepares you better for surprises. There are a lot less surprises. Yeah, all these are the same. All the rest are the same. So I'd see, okay, same thing, and then skip it. All right, and then let me go back to the PowerPoint. I went out of order here because it was just... But does this look familiar? This is cobalt-2 chloride. Cobalt-2 chloride, the blue stuff is anhydrous. Anhydrous means no water. You know what the pink stuff is? It's cobalt-2 chloride. What do we name this? Cobalt-2 chloride hexahydrate. And that's the pink stuff. And do you know what name they call this? They sell this commercially. This is solid. Actually, both of these are solid, though they look like liquids. You know what this is commercially called? We buy lots of this stuff. This is called Dryerite. And you know what we use Dryerite in? Our desiccators. And so this is our desiccant. So what we do is we put the blue cobalt-2 chloride anhydrous in there, and then that sucks the water out of the air. And then we know it goes bad when it turns pink. When it turns pink, it's gone bad. And you know what we do when it turns pink? We throw it in the oven to dry it. And so it dries off the water's hydration, and then after sitting in the oven for a while, it goes back to blue, and then we can reuse it. So this is great stuff because it's not one-time use. We just keep recycling it over and over again. So we don't have to buy it all the time. Okay, for the organics, what should you know? Probably some of the big ones, like you don't have to know ethane or benzene, but you should know methane, maybe propane, methane, ethane, propane, that's enough. Ethane, benzene. We'll do more organic nomenclature as we go along, but we'll try to keep it simple. Methane, ethane, propane. How many carbons in each? Right? Maybe butane. Butane might be good. Methane, ethane, propane, butane. For sure, you should know ethanol, grain alcohol, and methanol, wood alcohol. Now, we have two types of propanol. We have regular propanol, and we have isopropanol. Isopropanol is the alcohols on carbon 2. Regular propanol, the alcohols on carbon 1. You don't have to know these. Just know methanol and ethanol. You're going to have to know propanol and isopropyl alcohol later, but not now. You should know formic acid and what's this one? Acetic acid. You should know those two. Formic and acetic, or methanoic and ethanoic acid. And that's good. All right, since I have so limited time, and I need to talk about Chapter 4 since I don't want to get too far behind. I'm just going to talk about Chapter 4 here. The main topic of Chapter 4 is stoichiometry and solution stoichiometry. there are some subtopics that make things more complicated. We do this of pure substances. Sometimes we don't have to use the word pure. And mixtures. When we deal with mixtures, how do we deal with the composition of mixtures? The most common way we deal with the composition of mixtures is by percent by mass or percent by mole. It could be percent by mole for formulas, but most of the time it's percent by mass. For pure substances, we might have percent by mole for the composition of, let's say, water. But this is rare. This is much more common that we're going to encounter. There's going to be another percentage we're going to encounter in stoichiometry, and that is the percent, things called percent yield. Have you heard of that? Yeah, I think everybody's heard of percent yield. It's just different. And so we might be dealing with multiple percentages that we have to keep track of. That's all. And so the most complicated problems is you're given the mixture. So for example, they won't tell you 20 grams of oxygen. They'll say 20 grams of air. If you have 20 grams of air, how many grams of oxygen do you have? Can you use the 21% or do you have to use the 23%? You have to use the 23%. That kind of thing. So these percentages we have to keep track of. And this is why I spent so much time talking about percentages, parts per million, parts per billion, because you got to log those in your head as fractional things and then go on from there. And so we use percent yield in different ways. And we have limiting reagent, remember, LR, excess reagent, etc. We have those topics. And so we look at some of the most complicated stoichiometry. With stoichiometry, what you need the balanced chemical equation, right? And since I said, in Chem, at UCLA in Chem 1, this is all review. They wouldn't even talk about stoichiometry because they expect everybody to already know stoichiometry. And so what we might try to do is we might just try to review this. Since we're tight on time, we're going to just review it by looking at all the stoichiometry problems at the end of the book and seeing if we could figure those out without even having to read the chapter. We may have to read the chapter. Eventually, you're definitely going to have to read the chapter because there's going to be a lot of new stuff. A lot of those standard exercises are just regular stoichiometry problems. Okay, in stoichiometry, we need a balanced chemical equation. So these are just writing a balanced chemical equation. Limestone, calcium carbonates, heated calcine decomposes calcium oxide and carbon dioxide gas. So they tell us what the reactants and products are. All we have to do is balance it. And so the first series of questions are here. And then write chemical equations. So we have to write a balanced chemical equation again here. That's part of stoichiometry. And then we look at something like that. 3 astronauts aboard Apollo 13, which was launched in 1970, April 11th, and returned to Earth on April 17th, could sustain their breathing during the mission, in part because of lithium hydroxide canisters that were designed to remove exhaled CO2 from the air. CO2 can be toxic at high levels. They would get if they didn't remove the CO2, their blood pH would get too low. And they'd suffer the consequences of that. Solid lithium hydroxide reacts with CO2 to give solid lithium carbonate and water, with the assumption that an astronaut exhales approximately 1.00 kilograms of CO2 per day. What mass of lithium hydroxide was required to remove all the CO2 exhaled by the 3-member crew on their 6-day mission? This is actually not a difficult, this is just a standard stoichiometry. The difficult thing is just writing the equation, and this, I don't know why they put this in the advanced section. This is just a standard stoichiometry problem. And so what we'll look for is something with twists on it. Chalkboard chalk is made from calcium carbonate and calcium sulfate with minor impurities such as silicon dioxide or quartz, SiO2, or silicon 4 oxide. Silicon is a semi-metal, so you can either use ionic nomenclature, silicon Roman numeral 4 oxide, or molecular nomenclature, although it doesn't form molecules. Silicon dioxide is a network covalent solid. It's quartz, You've seen quartz crystals. Quartz crystals aren't molecules. Only the calcium carbonate reacts with dilute hydrochloric acid. So this is a mixture problem. So good, I have a mixture problem now. The mixture is going to contain calcium carbonate and some impurities like SiO2 and calcium sulfate. The calcium sulfate doesn't react with hydrochloric acid like barium sulfate. Did barium sulfate react with hydrochloric acid? No, there's no driving force. Same thing with calcium sulfate. What is the mass percent of calcium carbonate in piece of chalk? If a 3.28 gram sample, 3.28 gram sample yields 0.981 grams of CO2. So now we have something a bit more complex because now we have a couple of, extra steps that we have to do in here. And so the standard stoichiometry is, okay, we start off with a given. What is the given? Oops. And so this is just, this is an advanced problem, but the advanced problems are just like one extra step or two extra steps over a basic problem. And so what's our given? In stoichiometry, our given would be what? Well, we're given two givens, 3.28 gram sample. Well, the sample is not part of the equation. The given here is 0.981 grams of CO2. Now, what they're after is they're after the percent calcium carbonate in the chalk. And the percent calcium carbonate, this is going to be by mass, so it's an M over M. And so if we want percent calcium carbonate, then we need to know how many grams of calcium carbonate we have in the total grams of sample. The total grams of sample are 3.28 grams of sample. And this is going to be times 100%. And so what we're trying to figure out is the grams of calcium carbonate. That's what we're after. We can figure that out using stoichiometry here, because if we know how many grams of CO2, we're going to go from grams of CO2 to moles of CO2. And then from moles of CO2, we're going to go to moles of calcium carbonate. This is a 1-to-1 mole ratio. And then from moles of calcium carbonate, we're going to go to grams of calcium carbonate. And so this is a basic Chem 4 stoichiometry problem on the bottom. And what makes this an advanced Chem 1A problem is that we have to take this grams and then put it into the equation for percent. And you guys should be masters of percent, or at least understanding percentages, right? Or at least try to. If not, just work on it. Well, okay, we're out of time, but it's chapter 4 is this stoichiometry and the solution stoichiometry, like molarity and that kind of stuff. And so we'll look at molarity, which is another way to represent composition next time. Okay, my office hour is going to be in Chem 108 if you are planning. So I'll just meet you in Chem 108 if you